Let's welcome Ivica from EPFL, Lausanne. He's going to talk about the discovery of a novel type of a 3D connected network on the Trillium lattice, and what are the interesting physics arising out of frustration in that. And Ivica, it's over to you now.
Thank you, Yasir. Okay, so it's about the discovery of a novel type, and I will start with an introduction, which although everybody sort of is familiar with probably, I will go in a different direction in terms of basically emphasizing difficulties of material science point of view and trying to realize various theoretical models of highly frustrated systems, especially in the quantum regime. So in this case, a long time ago, Anderson sort of postulated the idea that on a frustrated triangular lattice, you will have this sort of entanglement of singlets, which then fluctuates on different bonds. But then it took basically 40 years to properly realize that model, right? So then in the 2003, this sort of organic-based triangular lattice compound has been sort of synthesized and sort of proved that it shows a really sort of spin liquid behavior. And then soon after, another well-known compound on a well-known frustrated lattice on a Kagome lattice has been delivered in form of Herbert-Smithite. But then again, although in the following years there was an immense amount of work done on that, still today there is a problem of this non-inversion between the copper site which form the Kagome lattice and then the zinc ions which sit between them, and which sort of influences the properties of this particular material. And then in the realm of 2D lattices, we have now also a lot of research on the Kitaev model type systems, where in 2007, I believe, Kitaev sort of proposed that you can have a frustration with if there is a bond selected interaction, and then later on it has been sort of proposed that this can be found in materials with strong spin orbit coupling, and then in 2016, ruthenium trichloride has been proposed to be a realization of that model. Now, still research is going on, and there are still problems of establishing, from the materials point of view, good materials which actually realize the Kitaev model without other problems. For instance, in ruthenium trichloride, there was a problem of stacking faults. And then there is always a question of the presence of normal Heisenberg interactions, which then move the materials away from the ideal case of Kitaev interactions. In 3D, it's not much better, I would say. You have on the left-hand side, you have the example of the hyperkagome lattice, which in this particular case is composed of iridium ions. And in this case, you have this strong spin orbit coupling, where the effective moment, spin 1/2 moment, is actually strongly coupled with lattice, and there is still inversion with sodium ions. So there are still, again, issues in realization of that model. On the right-hand side, there is a pyrochlore lattice, which has a long history, starting in 90s, and with the discovery of spin ices and all this beautiful emergent electrodynamics carrying magnetic monopoles. But there, again, one has to emphasize that that was realized in dysprosium and holmium, which have large magnetic moments, but only later there has been the realizations of materials with praseodymium, which has effective spin 1/2, and then there was starting with this publication substantial evidence of quantum spin liquid behavior in the pyrochlore lattice. So that leads us, the end of this introduction, that leads us to the topic of this discovery. And in the rest of the talk, I will try to explain the details of that discovery and what sort of how to place it in the current state of the research on quantum spin liquids, and especially what new this brings in and what future can be hoped for. Okay, so we start with this very short history of lung bayonites. We will explain something about these trillium lattices, detailed investigation on the nickel version of that, and then some other aspects of what we did. So lung bayonites are a family of minerals, and the name comes from a lung bayonite, which is basically this compound, potassium magnesium sulfate, discovered a long time ago and classified. And this family is basically following this structure, which is a cubic structure of P213 space group. Maybe the most important part is that that's non-centrosymmetric. And basically, this is how we actually ended up investigating lung bayonites, because we were working on this skermion compound, copper oxoselenate. And then we were looking at other magnetic carrying ion structures with the same space group. And then we stumbled upon the lung bayonites. The other characteristic features of the structure are that there are 2 octahedral sites which contain metal ions. So you can see them here. The octahedrons are not perfect, but they are almost perfect. But there is a slight rhombohedral distortion from the ideal dimensions. Then you have sulfates coordinated with 4 oxygens. So that forms a tetrahedron. And basically, this is where your interaction comes through. And then there is a cation, in this case, potassium, which is removed from this picture. If you do a little bit of research on what has been done on lung bayonites before, you will actually find very little. Actually, these guys were investigated in late 70s and through 80s in the context of renormalization group. So in the 70s, when the renormalization group theory has been developed, then there was a lot of investigation of magnetic properties in soft ferromagnets, searching for universal classes, critical exponents, and so on. And it seems that lung bayonites have been investigated in the same context, but now from ferroelastic and ferroelectric properties. And as you can see, some of them go through a series of structural transitions. And most of these transitions occur at relatively high temperatures, enough that they can be investigated with liquid nitrogen. So not much actually has been done at low temperatures. It has been either considered that there are no interactions, so it just behaves as a paramagnet, because maybe there were no shared oxygens between the metal ions, so it was considered that the interaction is too weak. Anyway, so no detailed investigations of magnetism on this family can be found. Okay, so we go a bit deeper into how this magnetic lattice looks like. It turns out that each magnetic site is actually forming something that is called a trillium lattice. In essence, the trillium lattice composes of triangles, equilateral triangles, which are joined in this way. So each node is connected with 3 of them, and they are forming this sort of fan-shaped structure with a chirality. And here you should be able to sort of grasp the idea of how this looks in 3D. So those two trillium lattices are interpenetrating, and you can see that each of them has this minimum sort of connection with 5 sites, right? Okay, so before going into the double trillium lattice situation, we can sort of look into what happens in the single trillium lattice. And the most known compound forming that lattice is this manganese silicide. And for this compound, more than one lecture can be sort of given. So here, just maybe the highlights are that there it has been found that you can have this pressure-induced quantum phase transition, and then there is this mysterious A phase. And then it turned out through a series of high-profile articles that this pressure-induced quantum phase transition supports non-Fermi liquid behavior. It has been looked into a lot in the most general way of how itinerant magnets behave in dirty and clean limit. While on the other hand, this A phase has been shown to actually represent now a huge field of investigation of skyrmion lattices in chiral magnets, and started the whole frenzy of skyrmions in much wider range of research in different materials. So following this the question of what happens in compounds with a single trillium lattice, there has been also some theoretical investigations of trying to see sort of how frustrated is this single trillium lattice. And long story short, it's frustrated, but sort of not enough. It leads in principle, it leads to a type of 120 degrees order. So where on the triangle, the moments point in sort of various directions relative to each other. So it seemed that it doesn't sort of bring too much excitement into the highly frustrated sort of research. Okay, so we are now focusing on the results of our investigation on the lung bainite, which contains nickel. And you can see here the reference. From the magnetization stability point of view, you can see that high temperature, it follows the nicely Curie-Weiss behavior with the slope corresponding to spin 1/2, which is an agreement with the nickel. And then it gives you the sort of average interaction between the moments of antiferromagnetic type, and then the size is roughly 18 Kelvin. As far as we could see, the behavior is isotropic above 2 Kelvin. And then if you look at the behavior in the magnetic field, you see that these points at different temperatures deviate first from significantly deviate from the Brillouin function, which is given by dashed lines, but also they deviate significantly from the solid lines, which are given by results of the calculation of the classical Monte Carlo, which means that at least partially there is a significant contribution from quantum renormalization. If you look at another thermodynamic part, which is specific heat, so here we have a comparison with a father compound, the magnesium one, a non-magnetic analog, and you can see that there is a strong deviation from the purely Flanonic behavior below, let's say, 20 Kelvin, which agrees with the Curie-Weiss value. And if you integrate all that, you can see that you basically recover the whole expected entropy in this compound. On top of this broad feature, there are these two small features designated with T star and T double star. And so one could ask itself, so whether this is impurity or this is something intrinsic. And we believe that this is actually intrinsic. So you can see here the comparison of specific heat on a powder and on a single crystal. And as a little bit later I will explain, this actually corresponds to something that we believe is a realization of a weak order here as a second order phase transition into an incommensurate structure, and then later there is a first order phase transition into a commensurate structure. If you look at at this peak, which we believe is a second order type, and if you sort of look into the total entropy released across this transition, you actually end up to be only 1%. So very, very small amount of freezing actually occurs at that transition. And if you look at the neutron diffraction at a low temperature, so this is well below these features, so 100 millikelvin, this is around here. You can see a series of peaks appearing below 1 inverse angstrom. Everything above is actually dominated by phonons, by nuclear Bragg peaks. And so although one cannot actually refine properly this structure, just extracting the position of peaks and extracting the cuvettes from Lebesgue fit actually indicates that we are not talking about a trivial one. So the Q vectors here as a satellites of nuclear Bragg peaks indicate sort of that the wavelength of this ordering is much it's larger than the unit cell. So in this context, we believe that really this represents sort of this series of second order into incommensurate structure, and then a first order into a commensurate structure, which then hits this 1/3 Q vector. Okay, and sort of one of the most relevant features from experimental point of view is investigation of μSR behavior, where typically this is a go no go test whether the system is ordered and not ordered, where the ordering typically shows up as wiggles in μSR, and here there are no wiggles, but the behavior at low temperature is actually rather non-trivial, where you actually need to use two components, and given that there are not many features in these curves, the sort of the modeling of that is sort of, it's not really unique. But the way that we did it actually shows that the relaxation rates of these two sort of components do show the typical behavior of a quantum spin liquid, with a plateau occurring at low temperature. But what is more important is that one component of the which actually is described with this beta 2 at low temperature hits this value of 2, exponent 2, which following this article has been indicated as a proof of an existence of a sea of singlets, which here and there release sort of unpaired electron, which then generates the dynamics of this type. And then further on this dynamic part, we also did the polarized neutrons, where you actually pick up only magnetic scattering, and that behavior is sort of rather oscillatory. You don't have the peaks appearing, and this behavior can be rather well reproduced with the quantum many-body calculations, which I think has been sort of lectured here by Johannes Reuter previously. And also, if you do the time of flight neutron scattering on powders, you obtain this result with no obvious gaps appearing at low energies, and sort of the energy scale which agrees with both results of specific heat and key device temperature. So in conclusion, although there is these small two features appearing at around 1 Kelvin, we believe that these features are actually have quite minor influence on the dominant behavior of this material, which is actually dominated by spin fluctuations. If you apply magnetic field, we did it for specific heat, you can see that these features disappear, but the overall shape is basically unchanged. And then at low temperature, if you look at the power law behavior, you always arrive at this exponent equal 2. So there is no development of exponential behavior, which would indicate that the system develops a gap in excitation spectrum. And then if you follow what happens with these features, you can develop this phase diagram, which then leads to the conclusion that basically above 4 Tesla, you are definitely in a purely dynamical phase without any indications of long range oil. Okay, so that was the majority of the experimental part, and now from the sort of conceptual point of view, these two interconnected trillium lattices, how are they interconnected? So from the DFT calculations, it has been extracted these sort of exchange interactions, and you have 5 of them. So this is a rather complicated network. But looking at the dominant ones, you can see that the 2 trillium lattices are these given by J3 and J5, colored by purple, and red, while the most dominant interaction is actually the green one, which interconnects 2 trillium lattices. So in a sense, from this point of view, one can look at what happens, what we have observed in 2 scenarios, right? So we have small order at the moment, we have strong fluctuations in the system. So we should be somewhere close to, we can say quantum phase critical quantum phase transition, where on the one hand side, you have basically dominant J4, which is the interaction between the trillium lattices. And if you look at it, this is basically J4 is forming a bipartite lattice. So that means that this is an antiferromagnet in this regime. On the other hand, if you set everything else to 0 and you have only J3 and J5, basically you will have 2 trillium lattices, which are basically not connected. So you could look at it from the point of view of single trillium lattice. And as we have shown, in principle, also there you can expect a long range order. So that means that in one scenario, we could be with this compound sitting quite close to this quantum critical point just by accident, right? On the other hand, there could be a possibility, and hopefully this could be even more interesting, is that actually there is a whole regime of values of J4, J3, and J5, which would give you this. We could call it a dressed quantum spin liquid state, where the singlets which form on J4 bonds are highly frustrated because of the presence of J3 and J5. But then because of the space group is non-center symmetric, everything is sort of chiral, everything is twisted. And sort of in the manner of the analogy with skyrmions, what you can actually have is that this non-chiral, the non-center symmetric space group is sort of mixing up these singlets and triplets in a way that the ground state actually has a little component of the triplet state, which means that every singlet is dressed a little bit with a moment, so it's non-zero, and then these moments are actually now coupling into a non-trivial lattices, which then can be in non-trivial way influenced by magnetic field, leading this to a fully dynamical state. Towards the end, we have also done time of flight experiments on singular crystals. And if you sort of look at that results, you can see that the features are completely non-dispersive. And they, if you look at this cut, you can compare that to the quantum many-body calculations, and the agreements are actually quite good. And we are still working on sort of quantifying that agreement. And basically, this is really coming towards the end, sort of what can be done in the future. And from the materials point of view, I think really this family offers an enormous potential. So potassium nickel sulfate as a sort of representative now of a quantum spin liquid behavior in a 3D regime can be expanded in so many ways. So you can change the alkali ion into all these ones. The 2+ magnetic ion can be changed into any other. Funny thing is that the copper does not work. For some reason, there is no reports of copper version of the potassium sulfate langbeinite. And then also the sulfate can be changed. You can see here many other versions which can be squeezed into this structure. We have investigated a couple of them. The cobalt version, the manganese version, which actually is one of the rare examples of where something has been done and some order has been found below 2 Kelvin. But you can see that the deviation from the key device occurs at much higher temperature. So the interactions must be much stronger. So that indicates that there is a wide temperature range where strong frustration-induced effects might be expected. There is also one example where we changed SO4 into a PO4 group. So that goes from SO4, which basically gives you two sites of magnetic ions in 2+. Now with the PO4, you can go into a 3+, 4+ combinations. So that means that now you are going back into a single trillium lattice state. And here you can also see that there is no indications of long range order. Now, because of the rare earths, you have the population of various crystal field levels. So the extraction of information is a bit more complicated, but still above 2 Kelvin, there is nothing to be seen. And also you can also imagine doping magnetic sites with non-magnetic magnesium. And just for the end, I will show you here sort of a list of all the compounds which are found on this web page on Wiki under Langbainites, and you can see that it's an enormous list that already exists. Actually, as far as I remember, it's not that all of them are synthesized, but some of them are actually just calculated, and of course, not all of them are magnetic. But this just shows that the potential to investigate the very, very sort of subtle features of frustration and quantum spin liquid behavior are really enormous. And sort of I think that these Langbainites really stand out if you sort of compare them to the what has been shown at the beginning of the presentation of comparison with other lattices which support quantum spin liquid behavior. It seems that Langbainites offer really, really sort of interesting future. And with this last slide, I would like to thank all the collaborators and you for listening.
Thank you, Ivica.
I hope I didn't go too far.
No, I think you convinced us that I changed the poem which we study in school, that the Langbainites are lovely, dark and deep, and that there are miles to go before we sleep. So
poetic.
From the audience, yeah.
Very nice talk. You have so many Mott insulators in this family. Is it possible to dope them and make them conducting, perhaps superconducting?
Well, I would say I would not dare to say no. On the other hand, the Hoping integrals I think are rather weak, right? So your T over U is probably rather large. I don't know. I would try if I would be sort of aiming at that and see what happens. I wouldn't hope too much, but I think one should try. There are so many surprises always in new materials discoveries. So so I didn't mention, but the preparation and sort of these compounds is rather simple. It's nothing it's nothing special. So powders have been prepared with the powder, sort of the solid state synthesis, and single crystals have been basically just melted the powder and then recrystallized. The problem is with the I think they do not really have a large temperature range where it melts before it starts to decompose, because SO4 and also PO4 like to fly out. So one needs to take care of all this, but it's rather simple to make them. In 3 days, you have a compound. So it's really easy to try stuff.
Arnab, please.
Hello, that was a very nice talk. This is Arnab Banerjee. So I have a quick question, and this is regarding the theory. So you flashed the single crystal data at the very end. And I was wondering that, do you have plans to do something like nonlinear Langevin dynamic analysis of this? Is that possible? Given that it's a 3D system, I think it's a little bit more difficult, but is that a possibility?
I would have to say that I do not know. I'm an experimentalist, sort of, solid state towards material science. So what is possible from the theoretical point of view, I don't dare to say, right? At the moment, together with Yasir and before mentioned Johannes Reuter, we are trying to basically look into this time of flight experiments on single crystals, and basically just try to see how much of all this is classical and how much of all this is quantum. But anything further than that, I think it's out of the scope for us at the moment.
Thanks.
Hello, here's Carlo. I would like to know, nickel is known for having strong on-site anisotropy.
Yes.
What about in this case?
Again, the question of anisotropy on the single ion could be addressed with ESR, and we did a little bit of that, and we didn't see anything sort of spectacular there, sort of that's really strongly anisotropic, right? The plot on the left sort of indicates that on the macroscopic scale, right? So the unit cell contains 8 of those, 4 plus 4, and on the macroscopic scale, we do not see anything weird, right? Everything is sort of seems to be equivalent. Whether whether individual ones really sort of are strongly anisotropic, it's hard to say. G factor is 2.34, so that indicates that it could be, but that is actually typical values for nickel. If you look at a little bit of nickels and ESR, it's not sort of strange to see it. So I would say that it's not anything special in terms of what could be expected from nickel, right? Now, if you look at cobalt, I would expect there to be much more strongly influenced there. But then again, there you actually have these structural phase transitions. And actually there, the suspect is SO4 group, which freezes. So you have some modes which fluctuates. And then when those freeze, you have the structure. So still at low temperature, one should be able to address the question of anisotropy by investigating the cobalt version. Right? For us, it seemed that nickel is as good as isotropic.
Thank you.
So if there are no further questions, then let's thank Ivica again. Thank you so much
everybody.
for this nice
talk.
Thank
you, Yasir.
Yeah, thank you.